Okay, well, let's begin. So motion in a vertical circle. You can see there's a little animation on the left. Obviously, you can't draw that. But what do you think the red arrow is? Why do you say that, Joey? Like, what gave you that idea? I shouldn't have said it like that, I guess. So, what gave you that idea? Because you're right. Yeah, it's going towards the center. Although, it's changing though, isn't it? Is that making you a bit nervous? Yeah? Is the centrifugal acceleration going to change in a vertical circle? We already know the speed changes, so is it okay if the acceleration changes? No. I mean, that certainly shows it. Well, let's take another step back. What do you think? What's the blue one here? That's gravity, right? So, what would you say about the blue and the red at the top? I mean, they're in the same direction. Would gravity help or hinder the centrifugal acceleration? It would help. Would it be a part of the centrifugal acceleration? Yeah, it would, right? And I guess you could also argue, well, it's part of it down here, but at the bottom, because the gravity is down, the actual centrifugal acceleration to maintain that speed would have to actually be greater to overcome that. It's kind of like the friction things down here, right? That's working against friction here, working against gravity here, but up here it's working with gravity, right? And if you can sort of keep that all in mind, I think you'll find these questions are relatively straightforward. Oh, we already talked about this, right? Oh yeah, this is that stupid day that I was experimenting with sound. Now it's just annoying. We already talked about what happens to the speed of the ball, right? At the start there. Oh, what about the tension in the string? It does. When is it greater? At the bottom. The tension in the string is that centrifugal acceleration. It's all blocked out for some reason now. Oh yeah. Draw that picture while I go do my test. That's the picture we got to talk about. Okay, so no doubt you're sort of wondering what all those subscripts and all that kind of stuff means, right? At the bottom here, Vmax, what would that stand for? Maximum velocity, and of course up here would be the minimum velocity. Would the velocity here and here be the same? And when I say velocity, that's just a bad, I shouldn't say it's a bad habit, but it's a habit. I'm really meaning speed, because clearly the velocity cannot be the same, because the velocity here is up and here the velocity is down, but the actual speed would be the same, right? Yeah, okay. So what about, well, Fw you know is weight force, right? So Fs1, Fs2, the string force, okay? It's really another way of describing the tension, right? And are those tensions the same? And the simple answer is no, they're not, right? Even if you just think about, like, take the rubber stopper and I go in a vertical circle like so, right? If I go slow enough, what happens to the tension at the top? It goes to zero, right? And even when that happens, there's still got to be tension at the bottom, right? Okay, so clearly those tensions are not the same. Okay, so because of gravity, the speed of the ball is not uniform. We've discussed that already. We just need to sort of formalize it. The ball accelerates on the downward path and decelerates on the upward path. So over here it speeds up. Here it slows down. Speed is at a minimum at the top, a maximum at the bottom. I think we've talked about that already. I think everyone gets that. Really, you're just saying, okay, I get it all, Mr. Bennett. Just give me the formulas so we can go do problems, right? That's what you really want to know. No? How about we just say you gave us the formulas and say we did the problems? That's the best option. Or D, none of the above. Okay, well, let's talk about the top. I'll let you write that down before I explain it, because it can be a bit confusing. Sometimes it's confusing to me. Okay, we know what these different things mean. FC1 simply refers to centripetal force 1. I guess you could say centripetal force T for top. Doesn't really matter, it's just a way of sort of describing it. Is equal to the string force, the tension at the top, plus the weight force. And that would be true whether they're in the same direction or not, right? We're just adding the vectors together. And that centripetal force is made up of, the centripetal force is mv squared over r. I'm going to put v min there because we're talking about the velocity at the top. And here I just basically plug that in between there, right? Okay, so let's do some more substitution here. Oh. Let me check my notes here. You guys jot that down there. There should be something else here. Maybe I'm supposed to write it myself. Okay, so let's look at the bottom here. The centripetal acceleration is equal to the string tension, but I subtract the weight force. Why? Opposite directions, right? And again, mv squared over r. This time we use our maximum velocity here, v max squared, and we're going to subtract. It'll all make sense at the end, don't worry. I looked ahead. I made sure I did it right. Okay. Is v max greater than v min? It has to be by definition. Therefore, the string tension 2 at the bottom must be greater than the string force at the top. And that's intuitive. I showed you with the rubber stopper. In other words, the string tension is greater at the bottom. Was there a string tension, was there a force in the loop-de-loop on the video? Is there a string tension? There has to be, yeah. So it's kind of a weird one, right? Because here, the string is actually pulling it into the center, whereas in that one, there's no, what's holding the, it's inertia, really, right? It's the normal force of the ramp on the car. It's actually inertia that's supplying that centripetal force. It's kind of one of those make your brain hurt kind of thing. I'm not sure what that's all about. Okay. This implies that there's some velocity below which the ball will not move in a circular path. The string will slacken at the ball's highest point. Will this play if I click on here? It's supposed to. It probably won't. Okay. What's the yellow here? The yellow is the centripetal force. What's the red? Gravity, right? And if the yellow goes to 0, actually, if the yellow goes to negative, I guess. If it goes to 0, there should just be enough, right? So they went to some physics dude, and what did he really want to know? Two things, really. What were the two things he really wanted to know? How fast do I need to go? Right? Because if he doesn't go fast enough, then that's going to happen. What happens if he went too fast? Too much G-force, blackout. When you say G-force, what does that mean? What does that really mean? Yeah, it's basically the centripetal acceleration. How much centripetal acceleration is there? Why does it cause you to black out? Yeah, the blood goes away from your head and it goes towards your extremities, right, to your feet. And fighter pilots, they actually wear pressurized suits, and when they go into that kind of spin move, the suit actually compresses their legs and forces the blood towards their head, trying to prevent that blacking out, because obviously they don't want their pilots crashing multi-million-dollar planes. I gotta go back. So, how do we figure out what that speed is? Okay, here's the math. The minimum value is when the string force is equal to 0, when the tension is equal to 0. At this time, the ball just makes it around the circle, because as it just goes around the top, right, when it gets to there, right, because of the angle, then the centripetal force becomes greater. So there's some speed that you have to go that gives you that centripetal force, string tension, sorry, not centripetal force, gives you that string tension equal to 0. What is that speed? Does anyone remember the formula that I said look over the guy's shoulder? There was a G in there, and there was a square root. And what was the other letter? R, yes. Square root and R and G. Let's just see where that comes from. Do you think pi is involved? So, at the top, don't write, just watch. I'll explain first. Centripetal force is equal to the string force plus the weight force. Weight force is mass times gravity. But remember, the string force, the tension must be 0. Well, that's nice. Just falls out, right? Centripetal force is mv squared over r. 0 disappears. What happens to the m's? Did they talk about the mass of the car at all in that video? They did, and that doesn't mean that they didn't worry about it, but they didn't talk about it. Masses cancel. V squared, or V min squared over R is equal to G. Rearrange that. V equals square root RG. Was that the formula over the guy's shoulder? Pretty sure it was. Please notice the mass of the car does not matter. The minimum speed that you have to go to maintain that circular motion or in a vertical circle, minimum speed is equal to the square root of R times G. Radius times gravity. There's only one thing that changes there. Gravity ain't changing. Radius. So if they wanted to break the record for the largest vertical circle done the loop-the-loop thing, they wanted to make a bigger circle, what would have to happen to the speed? Would it have to go in, up, or down, or stay the same? It would have to go up, right? The bigger the circle, the faster you have to go. And the faster you have to go, what would that do to the centripetal acceleration? Which is it not v squared over r? Am I right? It's been a while. Is that right? V squared over r? So if this velocity goes up, what happens to the centripetal acceleration? Goes up, which means the guy's likely to, guy or gal, stunt driver, likely to black out. So are they going to be able to do that on a much bigger circle? Probably not. Not without some sort of pressurized suit that keeps the blood from rushing from their head. Okay, if you haven't got that down already, you should do so. Am I good to go on? Okay, so this V is equal to the square root of RG. You're going to need that for vertical circles only. It has a special name. It's called the critical velocity. Why? Well, it's critical, especially if you're driving a car. Depends only on the radius of the circle and the acceleration of the gravity. It does not depend upon the mass of the object in motion.
It's only at the top.
That's how fast you have to be going to make it all the way around. If you're going faster than that at the bottom, what does that mean? I mean, you're still going in a circle at the bottom, right? Or anywhere else, besides exactly the top. It just means that you're actually going to be going faster, right? So they would have had to actually calculate when the guy did it there in the car. That's how fast he had to be going up here at the top. Would he have to enter the circle at a greater speed? Yes, he would, right? Because what's happening as he goes up, oops, he slows down, right? So they would have had to calculate how fast does he have to be going at the top, and then work backwards with the gravity and figure out how fast he has to be going at the bottom, so that in fact he does go that fast at the top. But again, does not depend upon mass. Now, a satellite in orbit around a planet moves with the critical velocity for its radius of orbit. So the moon actually moves with its critical velocity to maintain a circular path, or almost circular, around the Earth. What would happen if it was traveling at a faster speed? It would leave orbit. It would be no longer there, causing great problems for us here on Earth, I'm sure. The tides and whatnot, right?
And if it was traveling slower, what would happen? It would crash into us and burn, also causing great problems for us. That I am sure of. So yeah, anything that orbits has to be orbiting at a critical velocity. So when they sent that little doohickey up there to the comet, they got to figure out what the critical velocity is to get it in orbit. Haven't heard much of that in the news lately. I'm not really sure what's going on there. All these animations I'm supposed to show. You should note that, and this does pop up in the questions, okay? So please make a special sort of note here, Star. The radius of orbit for a satellite is equal to the radius of the planet plus its altitude, okay? So we're only talking about the radius of orbit. Our orbit is the key one here, and it's equal to R, that's an RE, radius of the Earth or whatever planet you happen to be orbiting, plus the altitude. Okay? So you need to know the radius of the Earth in some cases. And I know it's on that sheet there somewhere. I think it's 6,400 kilometers, if I'm not mistaken. It's not there. It'll pop up somewhere. Okay, you'll remember on that sample problem pack from the other day, I left out number 3. So let's go ahead and do number 3 right now. I don't imagine that there's going to be any problems. I think that you guys can solve problems that involve, come on. I'm pretty sure you can solve these kind of problems pretty easy, right? Like that's pretty straightforward. There's nothing, it's just going to say, what's the minute critical, what are the 2 things I can ask you for? There's only 2 things. What's the minimum speed? Or what would be the radius? Those are the only 2 things I could ask you for, right? So I don't expect there to be any problems with that. However, I can also ask you about tension at the top and tension at the bottom. That's probably why it was so slow, because this thing's still running in the background. Okay, so let me find those sample problems. Nope. Okay, so this is sample number 3. Does everyone have it? You should have it on a sheet that I gave you already. You shouldn't have to write it out. Okay, so we've got a mass of 0.5 kilograms. It's moving in UCM in a vertical circle. Now, a bit of a misnomer there. Is it technically uniform circular motion? Well, not really, right? But it's moving in circular motion. I'm not going to call it VCM, varying circular motion, I guess. But it's a vertical circle. The radius is 1.5. And just a little note here that on occasion they'll give you the diameter. So just make sure that you always are looking for radius. And the period is 0.5 seconds. Find the speed of the body in its orbit. Find the average centripetal force needed to maintain this motion. Find the string tension when the mass at the bottom and the string tension when the mass at the top. Okay, so the first couple are sort of introductory ones that you've already should be able to do. So we're trying to find the speed of the body in its orbit. V, and this is actually V bar. We're going to have to go back to the days of talking about average velocity. V bar is equal to 2 pi r over t from last week. Radius 1.5, period 0.5. Okay, that's just pretty much straightforward arithmetic. 18.8 meters per second. Everybody good? Part B asks for the average centripetal force. Now, why does it ask for average force? Why not just force? Because the force does what? It's changing, right? So we want to know the average centripetal force, which is Fc. I guess technically, if you want to get statistically technical, we'd have to put a bar over that. mv squared over r. How come the mass matters with the force? What does Newton's law say? F equals ma. The centripetal force is dependent upon the mass. The greater the mass, the greater the force. So the mass does matter here. 0.5, velocity of 18.8 squared, all over radius 1.5. Does the radius need to be in meters? Yes. If it's in centimeters, please convert. I get 118 newtons. Okay. I'm going to draw a circle. Where is it equal to exactly 118 newtons? The two sides, right you are, Jake. It's 118 there and 118 there. And here it's going to be greater than 118, and here it's going to be, oh, hang on. Hang on. Am I right? Let's come back to that. Let's come back to that. We'll fill it in after. The net force has to be enough to maintain UCM. Okay, so the net force, which is the centripetal force, which is equal to the string tension plus the wave force, must be equal to 118. Now, here's one of those dangerous situations where do the positive and negatives matter? Oh yeah, big time, right? Keep in mind, the string tension here must be, oh, I got it backwards again. String tension at the top is less. String tension at the bottom here is more, right? Always check when you're done. Is my string tension more at the bottom? Okay? Check your signs, make sure. If you always do that, you should be good. Okay, so I'm going to write Fs plus Fw equals 118. I'm looking for the string tension because that's what part C asks, right? What's the string tension at the mass at the bottom? So Fs plus 0.5 times minus 9.8 is equal to 118. Now, what is the direction of the force at the bottom? Up. Positive 118. String force, this is minus 4.9 is equal to 118. And when I take that minus 4.9 to the other side, the string tension becomes 118 plus 4.9. And I'm showing a little bit more work than normal here, but I want to make sure that it's clear. The string tension at the bottom is 122.9. Does that make sense? Remember, the string tension at the bottom must be greater. Is it greater? Yes. I'll let that just sink in for a second. The string tension at the bottom is going to be greater, which it is, 122.9. In fact, how much is the string tension going to be less than 118 at the top? It is if it's traveling at its critical velocity, but this one isn't. It's traveling faster than it has to be. Okay, this is not the critical velocity. In fact, you know what? We'll do that in part E. We'll figure out the critical velocity. I've never thought of that before. At the top, all of this is exactly the same, with one exception. What's the one exception here? The 118. Right? Why? Because it's down. Right? At the top, the 118 is down. Minus 118. Here it's plus 118. And I know that you guys can't do that copy and pasting, but I wanted to show you how much the same it is. So that's minus 118. This one should be as well. That one is. And when that minus 4.9 comes over, it's still plus. The only thing that changes here is the actual numerical answer. Minus 113.1. I'll pause and let you get that down and think about it. Let's add a question here. I'm going to do this for future generations as well. What would be the critical velocity? Well, it would be v is equal to square root of r times g. What's my radius? 1.5 meters. So 1.5 times 9.8 and take the square root of that. I get 3.8. 3.8 meters per second. That is the minimum speed it has to travel. So it's traveling much faster than it needs to, which is why there is tension in the string at the top, right? Does that make sense? Yeah? It's traveling much faster, right? Okay. All right. I'm going to give you the rest of this period. I realize that's not a whole lot of time. I'll give you tomorrow's period as well to work on some problems, get this straight in your head. It's a bit challenging, I get that, okay? Flying pig on Wednesday, don't miss that. And then we got to start talking about bank curves and such. This week's a full week, right? Okay, so that'll take a couple days. So you're looking at the circular motion test. I would say, if I had to guess today, I'd say about the Wednesday of the following week or so. So not this week, but Wednesday of the following next week. Okay. You're reading. I think bank curves is a one-day lesson. There's not a lot in here.